So the next thing we look at in the chi-square goodness of fit test is to carry out a significance test. So to carry out a significance test, we need to make sure that we check the conditions to perform a chi-square goodness of fit test. So the conditions that are involved with a chi-square goodness of fit test, we have the random condition, meaning that the data needs to come from a random sample or a randomized experiment. We have the large sample size condition, which means that all expected counts must be at least 5, and then the independence condition, which basically refers to if we're sampling without replacement, that the 10% condition must be true. So as far as the setup of this in a significance test, we have a null and alternative hypothesis here. So the null hypothesis would be is that the proportions that are given are all going to basically be equal to each other. The alternative is that one of the proportions, or at least one of the proportions, would be incorrect. And then here is the formula that we talked about from the previous lesson, and that's the formula for the chi-square statistic. So remember that a large chi-square statistic, a value that as the chi-square statistic value gets further and further away from zero, the greater the chance you have of getting a p-value that is small, where you would be rejecting the null hypothesis. So just some things to keep in mind with the chi-square statistic and performing a chi-square test. One is the chi-square test statistic compares observed and expected counts. You don't want to try to perform calculations with the observed and expected proportions. Common mistake that people make with a chi-square test. So you're comparing the counts, not the proportions. And then the other thing is, when checking the large sample size, just remember that it's the expected counts that have to be 5 or more, not the observed counts. So just two sort of things there that people commonly confuse with a significance test involving the chi-square goodness of fit test. So when we're talking about carrying out the test, so just kind of once again just talking about the conditions for this. So here's an example, and it says, as births are evenly distributed across days of the week, the one-way table below shows the distribution of births across the days of the week in a random sample of 140 births from local records in a large city. So you have the days of the week, obviously Sunday through Saturday. Does this provide significant evidence that local births are not equally likely on all days of the week? So here's the data that they collected from 140 births from Sunday through Saturday. So you can see here's the data that they recorded. So if we're talking about this in a four-step process type way, in the state part of this, we want to mention a couple things. First, obviously, we want to mention what the null and alternative hypothesis are. So the null hypothesis would be is that the distributions of the birthdays are evenly distributed across the days of the week. So in this case, 7 days in a week, 140 births, we would expect that each of these would be 20 across the board if that were true. The alternative is that maybe they're not evenly distributed. Maybe some, maybe one day or more than one day have births that are more likely than, say, other days. So we want to make sure we mention what the null and alternative hypothesis are first. Then we want to mention what the significance level is. In this case, we're going to do this at a 0.05 level, and then just kind of giving you this here at the bottom, and just sort of a different way of showing what the null and alternative hypothesis could be here. So in this case, we would say that the proportion of births on each of the days would be the same. An alternative would be to say that at least one of those proportions would not be 1/7. It would be something else there. So in the plan, we want to mention two things. One, we want to mention what kind of test we're going to do. This is a chi-square goodness of fit test. Then we want to check the conditions. We want to check first, obviously, that the births, the data was collected from a simple random sample. The large sample size, so expected counts. So if there's 140 births 7 days in a week, we would expect that each of the days would be 20. So since those counts would be obviously more than 5, we're okay there. And then if we're doing a random sample of 140 births, then we need to assume that there's at least 1,400 births in the local area, which if this is a large city, that would be a safe assumption to make there as well. Now I can move on to the do part. So in the do part, we want to do two things. We want to compute what the test statistic is, which in this case The test statistic for this would be 7.60, and then we also want to compute what the p-value is for this, and the p-value for this would be 0.269, and we'll talk about how to do that in your calculator here in a moment. So over here I have just an illustration of what the chi-square curve would look like based on the values that are given in the problem here, and then the conclusion for this would be because the p-value is greater than the significance level, we would fail to reject the null hypothesis, meaning these 140 births do not provide enough evidence to say that local births in this area are not evenly distributed across the days of the week. So if we were going to do this in the calculator, so I'm going to kind of pull up my calculator here, and then I'm going to go to stat, I'm going to go to edit, I'm going to put all the observed counts in L1, I'm going to put all the expected counts here in L2. So when I go to stat and I go to tests, and when I use my up arrow key, what I'm looking for here is a chi-square goodness of fit test, which is letter D. So I'm going to go to here, and then I have my observed counts in L1, I have my expected counts in L2. In this case, I have 6 degrees of freedom because there was 7 days of the week in this case. So when I go to calculate for this, here's the test statistic and here's the p-value. So that's how you can use your calculator to get the two values that you need from the do part in a real quick and easy way there. So that's just some different things with the calculator in regards to the test statistic and the p-value. So different question here, and it says biologists wish to cross pair of tobacco plants having genetic makeup G, uppercase G, lowercase g, indicating that each plant has one dominant gene, which in this case we'll say is uppercase G, and one recessive gene, which is lowercase g, for each color. Each offspring plant will receive one gene for color from each parent. The Punnett square suggests that the expected ratio of green-green to yellow-green to albino tobacco plants should be 1 to 2 to 1. In other words, the biologists predict that 25% of the offspring will be green, 50% will be yellow-green, and 25% will be albino. So it says to test their hypothesis about the distribution of offspring, the biologists made 84 randomly selected pairs. Of the 84 offspring, 23 of the plants were green, so here's your observed counts here. 50% or 50 were yellow-green and 11 were albino. Do these data differ significantly from what the biologists have predicted? Carry out the appropriate test at a 0.05 level to help answer the question. So if you're looking at just this from once again, a state plan do conclude type of format. So we want to mention first the null and alternative hypothesis here. So the null hypothesis is that the percentage of plants that would be green would be 25%, yellow-green would be 50%, albino would be 25%. The alternative is that one of those, or at least one of those predicted color percentages would be incorrect. And we're going to do this at a 0.05 significance level. So in the plan for this, we're going to do a chi-square goodness of fit test. We're going to check conditions, random condition here, large sample size, so we want to make sure that all the expected counts are at least 5. So if we did 84, if they had 84 plants altogether, and if I did the 25% for the green and albino, that would be 21 expected plants, and 50% for the yellow-green would be 42. And then independence, if they're choosing 84 plants, we need to assume that there's 840 plants that are in the population there. So as far as the do part goes, once again, test statistic for this, I'm going to do, this is going to come out to be 6.476 with a p-value that comes out to be roughly 0.0392, which is less than the significance level of 0.05. So that would give us reason to reject the null hypothesis and give us evidence that the biologist's hypothesized distribution for the color of the tobacco plant offspring is in fact incorrect. So once again, if we're talking about the calculator for this kind of question, so I put all these data values in L3 and L4 when I did this. So here over in L3, I have the observed counts. L4, I have the expected counts. So I'm going to go to Stat, I'm going to go to Tests, I'm going to go to letter D for the chi-square goodness of fit test, and then I want to change my observed counts to L3. I'm going to put my expected counts in L4. Now this, because there was only 3 categories, this has 2 degrees of freedom. And then when I go to calculate, so here's the test statistic and here's the p-value that goes with that. So that's just, once again, just how you would do that in your calculator. So just as a follow-up, so whenever you're rejecting the null hypothesis, one of the things that in a chi-square goodness of fit test, one of the things that you want to look at is some reasons behind why is the null hypothesis being rejected. And the thing that you want to analyze when you do that is what of each of the different categories that you have, which one seems to give the biggest difference between what was observed versus what was expected. So in this last example that we just did, you can see here that the biggest difference in what was observed versus what was expected was in this albino group. The difference there was 10. So the suspicion here is that because this value, or because these two values were so different from each other, you can see that just the 4.762, the makeup of the test statistic, the majority of that 6.476 came from just that difference is there in the albino group. That was probably the reason that the null hypothesis was rejected in this case. Now, in order for us to be able to verify that mathematically speaking, what we would need to do is we would need to perform a significance test just for that particular group of data, just for the albino group, if we wanted to in fact do that to verify. Not something that's necessary, but it is important that you should follow up when you reject the null hypothesis. You should look at your data values to see which of the categories do you seem to think would give you the best reasons for why the null hypothesis was rejected. So last example here, and the question says, in his book Outliers, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on his chance to make it to the highest levels of the game. Specifically, January 1st is the cutoff date for youth leagues in Canada. Players born in January will be competing against players up to 12 months younger. The older players tend to be bigger, stronger, and more coordinated, and hence get more playing time, more coaching, and have a better chance of being successful. To see if birth date is related to success, a random sample of 80 NHL players from the 2009-2010 season was selected, and their birthdays were recorded. Overall, 32 were born in the first quarter of the year. That means they were born between January and March. 20 were born in the second quarter of the year, so that's from April through June. 16 in the third quarter, so that would be from July through September, and then 12 in the fourth quarter, which would be from October through December. Does this provide convincing evidence that the birthdays of NHL players are not uniformly distributed throughout the year? So for this question here, the null hypothesis for this would be that the birthdays of the NHL players are equally likely to occur in each quarter of the year. Whereas the alternative would be is that they're not equally likely to occur. So we're going to do this at a 5% significance level. The plan for this, so we're going to do a chi-square goodness of fit test. Conditions we want to check. So the data came from a simple random sample of 80 NHL players. The large sample size for this, if birthdays are equally likely to be in each quarter, then if they sampled 80 players, we would expect 20 birthdays in each of the 4 quarters of the year. So since all of those counts are 5 or more, we're good with the large sample size. And then independence, if we're sampling 80 players, we need to assume that there's at least 800 players in the NHL, which in that particular season there were a total of 879 NHL players. So the condition for independence is met there. So the test statistic for this would be 11.2. The p-value for this would be 0.01. So the conclusion for this is that because the p-value is less than the significance level, we will reject the null hypothesis. And based on this evidence, we'll conclude that the birthdays of NHL players are not uniformly distributed throughout the year. So just once again talking calculator with this here. So I took these numbers and I stored them in the L5 and L6 columns of my calculator here. So if I scroll over to L5, so here's the birthdays by quarter: first quarter, second quarter, third quarter, fourth quarter, and this would be the expected counts if they were equally distributed. So once again, I'm going to go to Stat, I'm going to go to Tests, I'm going to go to letter D for the chi-square goodness of fit test, and I'm going to put in the observed counts in L5. I'm going to put the expected counts in L6. In this case, because there were 4 quarters, that leaves me with 3 degrees of freedom. So when I calculate this, I get a test statistic of 11.2, and there's the p-value 0.01. So that basically covers all the different things that we're going to look at with what's called a chi-square goodness of fit test. So what we'll kind of move into next is some different types of chi-square tests, one of which has to do with what's called a chi-square test for independence, as well as what's called a chi-square test for association.